Hello, everyone. So welcome to today's webinar. I am Matt Chan. So today we'll just go over Amesim and I want to show you guys how we can benefit from this industry-leading system simulation software and maybe get away from your day-to-day workflow on like maybe spreadsheets or your personal codes, etc. So here is today's agenda. First, I would like to give you guys a brief introduction on our company background. Then we'll begin by looking at some key industry challenges and business impact. And then we'll talk about how to find a new way forward with Siemens, especially on system simulation. And then we'll also talk about how Amesim can play a pivotal role in modeling mechatronic system. Last but not least, I would like to answer some of you guys' questions. You guys can put in a chat and I'll answer all of them at the end of the presentation. So before covering Amesim, let's talk about our company background. So we are SDA Software, which is a sister company of SDA. SDA is a structural design and analysis consulting firm, which provides expert simulation and design consulting services to the aerospace industry in general. And on the other hand, SDA Software is Siemens' value-added software reseller. We provide sales for CAE and CAD softwares. They're all listed on the right-hand side. We also provide training for FEMAT with Annex Nastran and also with FiberSim. So let's first look at industry challenges and business impacts. So nowadays, across all industries, we're seeing four major trends that have drastic impacts on how products are being developed. The first major trend is the shift from products being primarily mechanical devices to smart systems. That basically brings mechanical, electrical, and controls all together. For example, the environmental control in your car, they're slowly changing from like the old mechanical knobs into like buttons on the touch screen, like in a Tesla. And in the second major trend is the emphasis on new materials and new manufacturing processes. This includes the use of composite materials. When maybe your engineer is designing a brand new product, you may consider Kevlar, carbon fiber, etc. And your engineer might be also considering using additive manufacturing as a way to create parts that were maybe it was impossible to create beforehand or just too expensive to manufacture with the traditional approach like a CNC machine. And the third major trend is the increased demand for customization. This is partially driven by globalization, where your company might have a lot of customers coming from different countries or regions, and usually they have different preferences. A good example would be EU has different regulations than the US regulation. As an international company, you have to tackle that specifically. The final trend covers the evolution of internet connectivities, leading to the idea of system of systems and Internet of Things. So with that being said, the world is constantly seeking for complex systems, which provides advanced functionality like self-driving cars, eVTOL, etc. Therefore, today, engineering decisions are fundamentally involving system knowledge, and most companies are at different level of implementing system engineering and system simulation. As shown here, when you implementing these type of system simulations, there are always question needs to be addressed in any product development cycle. So for example, how can your engineer make accurate engineering decisions early on in your design phase so that you can minimize any issues or pitfalls later down the road? Or how can your engineer minimize the use of expensive prototyping? This is usually where system simulation software shines. They allow your engineer to effectively explore design space and forecast performance or pitfalls. And lastly, how can your engineer verify virtually that you have a complete system, not just functional components? It is crucial to ensure the components don't just work individually, but they work collectively as a system. So with all these questions in mind, Siemens provides Amesim as a flagship system simulation solution to tackle all these different questions. So especially when nowadays innovation is actually happening more and more at the system level. In fact, over 50% of the innovation is happening at the system level where different technology converge. The perfect example would be the adaptive cruise control, lane assist, or parking assist in your day-to-day vehicle. These technology differentiators are mainly innovations on the system level involving different subsystems like vehicle dynamics, electronics, and also software. But these implementations of these functionalities requires comprehensive knowledge on the overall system and also subsystem. So the ultimate question is, how do we make system knowledge something that is accessible to every engineer's daily work? And to do so, we need to hide the inherent complexity. And with this philosophy, Amesim is designed to be an engineer-friendly software where it's quite easy to pick up even if you don't have a lot of system engineering background. But yet there's another challenge is to get this to mainstream. This requires that everyone throughout the product lifecycle to be able to understand the dependency between components and evaluate the impact of change across the entire system when they implement changes. This is system engineers has basically been practicing this type of knowledge or exercise for years, but it is time for components engineer to leverage their expertise on the component level to the system level. So with that being said, let's see how Siemens approaches system simulation. First, I would just like to briefly talk about Simcenter. So Simcenter is the simulation portfolio for developing and evaluating your virtual representation of your product. Simcenter offers the best-in-class CAE simulation, system simulation, and testing solutions, as well as design exploration and analytics. And all these different types of softwares can be managed in the product lifecycle management context using the Siemens Teamcenter software to support the engineering and also the development of your complex systems. So now let's look closer at the simulation category for system simulations. Typical CAE solutions are quite heavily dependent on the available geometry, but Amesim does system modeling in a different fashion. So the approach is, in theory, is quite simple. So by creating 1D models based on physical equations, one can create a library of components with validated physical behavior. The physics embedded in these components can then be used to calculate how energy will flow from one component to another, and how this energy can later convert it into maybe heat, motion, or even chemical reaction. And these 1D model can be easily put together, a complete system model as well. And moreover, these 1D model can also be used for maybe a 3D code simulation and control strategy validation as well. So right now, let me just provide some background for Amesim. Simcenter Amesim is an integrated and scalable system simulation platform. It allows system simulation engineer to virtually assess and optimize performance of a system. It can basically boost the overall system simulation productivity from the early stages, like conceptual design, all the way to your final performance validation or your control calibration maybe. And Amesim contains ready-to-use multi-physics libraries combined with the industry-oriented solutions. And with the powerful platform capability, system simulation engineer or analyst can rapidly create like models and perform analysis for your system. And Amesim itself is also an open environment that can be easily integrated into enterprise processes since it can couple with major CAE, CAD, or some other control packages as well. So for example, you can interpolate with the functional markup interface known as FMI, or you can use Modelica, the language, to code your own components as well. And then you can also connect it with other Simcenter solutions like StoreCCM Plus, which is Siemens' flagship computational fluid dynamics software. And then you can also, of course, do it with Teamcenter to do your PLM. And besides that, Amesim is also available on Rescale, which is a cloud platform. If you need a lot of intense computational resources for a simulation, maybe you have thousands of Monte Carlo simulation to disperse. But in a nutshell, Amesim connects simulations of multiple domain of physics together into one system. This is possible because Amesim essentially solves for power and energy, and then the energy is transformed and converted throughout the system. Because the energy is conserved throughout the system, you can extract transient system level performance and even interactions to gain valuable insights. This can help your engineers to understand how the component or the system, how they will behave in real life. So moving on, Amesim also captures complex equations in easy to use icons and simulate the combination of physical models and control models together. And these equations are usually written as time dependent so that your engineer can assess the transient performance of the complex system. Right here, we're looking at three fundamental domains. Each of them are showing their corresponding equations and their physical icon representation. And we see that the physical icons representation is simplifying the equation into easy to read icons. This actually provides tremendous value to your system simulation workflow because with Amesim, you can now move away from like spreadsheet math and Excel, like doing like for me, I did buoyancy calculation before I even touched Amesim, and like you can hard code like complex equations for your system, like in MATLAB or Python, or even Fortran, depends like what you're used to. And these processes usually have a lot of like what I call development overhead, which requires a lot of resources, time, and most of the time they're prone to bugs. And your engineer would spend a good bit of time to iron out the nuances in the code or the spreadsheet. Even then, these spreadsheets or codes are not standardized. So if you have another group of engineers trying to reuse a spreadsheet or code, most likely they will have to get a hold of the creator just to understand how the spreadsheet works or the code, how it's laid out. And this inherently will introduce more communication overhead within your product development cycle. So with this simplification embedded in Amesim, engineers simply just need to understand like the input and output variables of each component chosen when they implement changes to the system, and then they can directly evaluate the impact of change. So like I said before, one of the benefits of Amesim is that it has an extensive library of validated multi-physics model. And with the extensive libraries, your engineer most likely will not need to write their own equations anymore. But the Amesim actually does have the option to. But Amesim actually offers a large set of libraries with more than 6,500 components that have been developed and validated in cooperation with industry partners. So here are just some examples of for the libraries. We have fluids, mechanics, electrics, thermodynamics, even engine and control. And each box here, there's a lot of sub-libraries that is related to uh, the main library. And these are all ready to use libraries. Any of these libraries would take a lot of time or investment for you or your company to develop from scratch. So it's really great if you can take advantage of these ready to use libraries or even the industry oriented solution to perform system simulations because they're tailored to specific industries like aerospace, automotive, and marine applications. And with these libraries, Amesim were able to create higher fidelity models to predict advanced dynamic with a shorter turnaround time. So like I said before, Amesim offers the capability or ability for you to simulate a wide range of different physics, but also scale it to different fidelity for each component. So each level of component, each level of fidelity here is shown, and they're like they have different like purposes. So for example, the functional model is great for performance-related simulation, where you don't involve as much physics as the physical model. And of course, the physical model is great for a dynamic or transient model since it retains a lot of the physics. And whenever you want to observe like time response of the components, then physics model is the way to go. And besides that, like Amesim also allows your engineer to define their own components. You can do it by the block diagram approach right here, or you can just go to the submodel editor and edit it on the programming level. So right here, I just wanted to like show an example of a thermal management model of a hybrid vehicle. Um, the Amesim project diagram is color coded based on their domain of physics, and the color scheme is shown on the left-hand side. You can see that the electric components are in purple. You have fluid and hydraulics are in blue, and mechanical components are in green, and you have like thermal components in brown, and finally you have control elements are in red, and it's really easy to read and dissect within your project diagram. And the key takeaway here is AIMSIM allows you to simulate all these different type of physics in a single location, and which is very important for advanced systems like thermal management shown here, because in thermal management, you could have thermal contribution from so many different sources that would make up the total thermal performance of a vehicle. And another nice things about AIMSIM is that it also allows you to go even a step further by coupling a more detailed analysis tools like 3D computational fluid dynamics, known as CFD, for detailed fluid performance, or finite element analysis, known as FEA, for structural analysis, load, etc. And the most important thing here for your control engineer is the red connection right here, that your control engineers can build basic control algorithms in AIMSIM, or you can also implement or import some other control algorithms from other tools as well. That's also a function you can do. And before moving on to mechatronic system simulation, I'd like to share some industry examples. So in the aerospace-oriented solution, it offers a broad range of application for you to do with the specific toolbox. You can do fuel systems. You can also simulate the flight dynamics of your vehicle, shown in the slides right here. But you can do way more than just what I'm showing here. You can also use Amesim to do maybe your aircraft engine performance, your landing gear, how you actuate your landing gear, or flight control, etc. And in the marine application, there's a specialized toolbox that offers advanced models like ship resistant, propeller, and sea state. And these models enable a streamlined marine workflow for engineer to simulate and evaluate the ship performance easily. Your engineer can explore design by simply just importing data from different sources. Like if you guys already done some experiments, then you can import in some experimental data, or you did some CFD, you can do CFD results, or just some legacy data is also an option for you to explore. This is the last industry example I'll talk about. So the automotive-oriented solution provides actually quite good capability in thermal modeling, like the thermal management we just looked at. It also offers internal combustion, fuel system, and these capability allows Amesim to generate a predictive model of your engine, and the impact of change from Amesim will provide design feedback to your design engineer so that they can make informed engineering decisions on maybe the next iteration for your design cycle. So now let's look at how Amesim plays an essential role in mechatronic system simulation. So let's talk about what is a mechatronic system. So in simple terms, a mechatronic system is the synergistic combination of mechanical, electronic, control, and software engineering. And oftentimes, engineers would integrate simulations, sensors, control module, or even more other stuff into an advanced mechatronic system. So here is an example of a mechatronic system. This is an electro-hydraulic power steering system. Now, if we take a closer look, we can see that it is comprised of different basic systems, and the basic systems are listed on the left-hand side, and they're highlighted on the right-hand side. We can see that the control components are in red, the electrical components are in pink, and hydraulic and pneumatic components are in blue. And then finally, the mechanical components are in lime green. And all these basic system has to work together to make up the power steering system. As we stated earlier, it is critical to optimize your design early on whenever your system is still conceptual. But there are some questions needs to be answered during this conceptual stage. So first of all, can we build a complete system uh, with a CAD-based software? Well, the answer is actually no. Most likely, this early on in your design cycle, you have minimal CAD data or you have no CAD data. Um, and even if you do have CAD data, it might change in the next 10 iteration drastically. So we need a new way to model that. And the second question is, can we simulate a complete system within an acceptable amount of time, especially in 3D? Well, the answer is no. Whenever you do a 3D software, it requires a lot of computational resources and is not feasible to do a complete system. So now we need a different approach to model this power steering system. One that allows us to pre-design, choose an architect. Where do you want to go with hydraulic, pneumatic, what sort of like electrical component you want, or something else. And you also need one to able to assess the key function of the system. So again, right here, I'm still using the power steering system as the example here. When we're designing an optimal system, there are typical issues that your engineer should account for. For example, what is the response time of the system, or is there any risk of vibration? In order to explore or address these type of issues, Amesim operates under a couple key concepts. So Amesim can be used to create plant models shown here um, to describe the physical behavior of individual components. And right here, for example, we have mechanical, electrical, and hydraulic systems. And then you can assess the physical behavior individually in these plant models. And then these plant models can be connected through the control model to form the complete system. And finally, your system engineer can simulate and assess the system response from the embedded multiphysics in your model. As a result, Amesim creates a complete multi-domain system simulation model that can virtually represent your power steering system. And yet steering is only part of the entire vehicle, so you can definitely scale this all the way to a full vehicle system simulation model. And then this power steering system basically just become a small component of the bigger system among all the other subsystems. So hopefully this example is clear and show you guys how you can approach a mechatronic system with Amesim. This is the last slide for today. So this, I know we blocked this for an hour, but this actually is intended to be a little bit more short, more so on like a big picture and overview. Well, thank you guys for listening to today's webinar. Let me check the chat, see if we can find any questions. And feel free to ask any questions right now. Okay, I see a question right here. Um, how does AIMSIM compare to Simulink? So in my opinion, it really depends on your main focus. Simulink, of course, is a good tool for control and signal processing. It gives you a lot of freedom too to create your own plant models from scratch using the block diagram. The only downside for that is it does take a decent amount of time to develop your own library or your own models. And a lot of times after you develop them, you still need to validate them. So it's a long process and a lot of investment. The competitive edge for Amesim, it really comes from the ready-to-use library, like I just mentioned, and it's actually quite component engineer friendly. A lot of plug and play. For example, you have fluid system engineers. They can do pipe flows by just swapping different junctions, bends, and your fluid engineers don't really need to worry about configuring the pipe components, but more so worry on the configuration of the pipe, like the length on each end for your L-shaped elbow, for example, and he doesn't have to worry about building the component from scratch. Okay, I see another one. How long would it take to spin up to speed? Um, it really shouldn't take too long. If your system engineer or system simulation engineer has experience on other softwares like MATLAB or Demola. In my opinion, I believe Amesim has a lower barrier to entry compared to other software, since, like I said before, it is partially designed for component engineer to be able to plug and play. And for for I guess for experienced system engineers, I would expect like maybe a week or two at max, depending if your engineer is able to commit full time on picking it up, because obviously your engineer might have other tasks as well. And if you're uh, asking for your component engineer, I also expect something similar, since, like I said, your component engineer most likely is not building the system model, but rather going into manipulating some configuration, like they implement a new valve for your pipe flow or pipe system, then he can easily go in and just swap a component. So it shouldn't take that long. Um, all right, I think we're coming up to the 45 minutes mark, or actually 30 minutes mark, sorry. Um, If you guys have any technical questions, feel free to reach out to the support at SDA Software email. And also, if you guys have any sales questions, feel free to reach out to the sales at sdasoftware.com. Well, thank you. Thank you guys for your time. I think this is it.